So here's my failed attempt at trying to regulate the output with some kind of active or dynamic setup. So I'm trying to walk away from total passive circuit, total solid state, in which in which all of the components are retain their values over the simulation period. Instead, I'm trying to find a way to make at least some of the components dynamically alterable over time so that I can regulate the output. The whole point here was to try to regulate the output, and I failed. Instead of regulate as in fine-tune and reduce, because the way the circuit works, you increase the size of the capacitances in the analog computer, and that raises the outcome in incremental steps that are quite large. And if you want to fine-tune in between those incrementally large steps, how do you do it? So I thought pulse width modulation would serve as a way to do it, but I haven't figured out yet how to do that. In this particular instance, I attempted to do that by putting in switched capacitors. It's a standard component in microcap, and it even exists in the real world. Maybe not at the frequency that I put it at and the resistances I put it at. I fine-tuned it for my needs to try to adapt it, whether or not it actually can be adapted in the manner that I did so. And I'll show you in a minute how I customize the macro. I could even show you what the standard conventional model is. Oh boy, I'm losing my voice already. Okay, so here I did 4 versions because instead of it diminishing the output, it actually increased it, and it made it unidirectional in a positive polarity on the virtual oscilloscope tracing, spikes, and what else? It seemed to suppress the buildup is what it did, and that's why the spikes, the peak-to-peak spikes, got bigger. Why they went unidirectional, I have no idea. It's almost as if it recoiled, but it did so at a particular frequency, the frequency that I set the sample rate of the switching capacitor at. Now, sample rate simply means the cycle time, and it's almost like a duty cycle variety of cycle time, because, it is, actually. It's 50% on, 50% off. In other words, the capacitor grounds itself out for 50% of the cycle and does not ground itself out for the other 50% of the cycle. And the sample time, or F sample in this case, which I'll get to in a minute, is down here. I customized it for all 3. That's your total cycle time, and then it's 50% duty cycle within that cycle time that you ground or not ground the capacitor. Now you ground both ends, and the grounding procedure is done through resistors. I should be showing you darn it. I should be showing you while I talk to you about it. All right, where are you? Okay, so this is what it looks like, the macro, and it uses these resistors. Phi bar is the value of these 2 resistors, while phi is the value of these 2. And they swap during each half of the sample time. They change positions. And so obviously, and what their value is the resistance for off and the resistance for on. So I have 1e to the negative 15 for on resistance and 1e to the positive 100 for the off position. That's not standard. The sample time is also not standard. It's 3e to the 11 hertz, or 300 gigahertz. But I found that was the incorrect sample time, and then I had to customize it in the circuit. But I just leave this the way it is, because I figured I might as well make it something and then define it for each circuit per need. But I made it 10 micro farads capacitance value, and that I can also customize per need. by making defined statements in the schematic. See, I didn't like the standard version because the standard version had resistances so low on the off that I found leakage occurred, so that regardless of which half of the sample period, it totally grounded out, and sufficiently enough that the overunity didn't build up. It never happened. So this was a nice way to shut it off, was to use a standardized switching capacitor, because it was off all the time. Well, I could have used I could have just grounded. You could put in switches with grounds on either side of the capacitor for all you know. Why do it this way? And that's another way to do it. I'm not sure how to do that, but we'll get to that in a minute. Or we'll get to that in some other video. Now let's see, I gotta find my position here in the lecture. I gotta go down here. Okay, so this is the node voltages of which version is this? A. This is the first version in which I just take the schematic as it is without making changes to it, because I found something interesting happen. If I increase my load within a certain limit, I can increase my output. I increase the node voltages and I increase the amperage and the voltage going through the load within a certain limit. If I overdo it, it kills the overunity and the thing goes dead. So I just picked arbitrary values for my three different loads, my capacitive load, my inductive load, and my resistive load, not knowing anything what I was doing. And prior to putting in these switching capacitors, just having normal capacitors short out both sides of each of the three transformers. But then when I played with these load values, I discovered I was increasing my output in only two instances, actually. When I increased my capacitive load, I actually decreased my output. But when I increased my inductive load and my resistive load, I actually increased my output. So only two of the three instances did I actually increase my output. The other one, the capacitive load, I diminished my output. But I found that quite fascinating, because we've heard stories like that. Oh, if you increase the load, the output goes with it, also goes up to match. And I thought, oh, cool, I kind of did that within certain limits. Because if I went too far, it just killed the thing. In fact, I was only able to increase the capacitive load by a minor amount by comparison to the other two loads, because I already arbitrarily reached almost my max before I killed the thing. So let's increase the size of this, if I can find where my cursor is. Ooh, cursor. Zoom in here. So my defined sample is 2.999 e to the 10 hertz. So what would that be? That would be 29.99 gigahertz, I believe, if I'm correct. And, oh, why is it, oh, can I move this thing? No. Oh, wait a minute, I can. I thought I could. So much for that. I can't move it. Oh, there, it moved. It took a while. Okay. Well, I got a slow computer. That's my problem, huh? Come on. Move. Move your little butt. Or move your big butt, as the case may be. Wow, this takes a long time. That's what happens when you're poor and impoverished and have to deal with a laptop working Windows XP. Okay, don't move. See if I care. Good grief. Oh well. So you can see I got up to teravolts on my nodes here. That's pretty awesome. Okay, now I'm done with that. Boy, that wasn't much. Let's go back to... Boy, that wasn't working. Come on, come on. Go away. Go away. Okay. So now let's move on to the next slide. That is the wrong slide. Okay, and that's the schematic. Okay, I got to back up now. So that's the schematic. And then let's see. Yeah, I better not move in. Now, here's the resistive load, 1 kiloohm. And as you can see, the peak almost reaches 225,000 amps. And they're unidirectional. Here's the baseline, is 0 amps. Nothing noticeably goes negative. Actually, when you zoom into this thing, it's right in here, in what looks like flatline, it's actually going downwards. And it doesn't start to go up here. It's going up all along, always at the sample period, except they're much smaller. In fact, there's a group of spikes over here that are much smaller. And then the rest of the way down to the beginning of the simulation, they're all the same. They're in the nano range of amperage. All these little peaks that go upwards. So if you zoom into this thing, you do find things are going in the opposite direction. But it's almost as if, but that's the way a diode works. It represses one direction, relatively speaking. It's never absolute. While in the direction you want it, it predominates your flow of current. So it's almost behaving like a diode, which means it's not a variable capacitor, it's a varactor, because a varactor is a diode of a type. It's a capacitive diode. So this is really functioning now like a varactor. That might be why I'm getting such crazy results. So I found I could increase my range to 463 picoseconds. If I go any higher, I get matrix's singular error, and that tells me that the next group of spikes, you see, the reason why the node voltages were higher than normal is because it's getting ready for a big, massive lurch of a spike greater than before. That's usually what happens with this thing. So it's warning you. So I couldn't go to 464 picoseconds because the simulator maxed out at matrix is singular, which tells me that the spikes became so much higher than this that when it tries to approximate and evaluate an approximate outcome, it can't, because the values are so large and the circuit's not perfectly designed for higher values, that the matrix, it does matrix algebra to approximate the outcome. The matrix is, what is it called? Indeterminate, because it evaluates to 0, and so it cannot take the inverse matrix, and because it cannot take the inverse matrix, it fails to converge. If you get a divergence when you approximate something, then you can't determine what you are approximating, because the outcome keeps going higher and lower to a greater and greater degree away from midline, away from 0, away from balance. I found this out when I was approximating polynomials in one unknown in my study of the golden ratio, discovering that there are infinitely many golden ratios in theory, although there's only 5 of them in actuality, and 5 silver ratios in actuality. But for the golden ratios, there's theoretically an infinite quantity, and each one is a ordered polynomial. So we use the second ordered polynomial. X squared is the highest value of ours, which gives us the golden ratio that we are familiar with. But that's only one. There are infinitely many in theory. I spent 3 years studying that. 20 years, more than 20 years ago. I stopped studying it in 1997. And what was I going to say? So when I was approximating the roots of those polynomials, I studying all kinds of techniques, various techniques. It was unbelievable, each different technique I came up with. A geometric technique, a counting technique, trial and error technique, and a trigonometric technique, all kinds of techniques. And all you can do is approximate. You can't come up with a strict answer, but sometimes I'd come up with goofy varieties of polynomials that could not converge. And so, see, convergence means what happens is there are techniques actually for approximating any root of a number, like the fourth root of a number. Like when you take your pocket calculator, there's ways of expressing the algebraic expression of finding the root of a square root, let's say, or a cube root, that is not a straightforward algebraic expression. What it is you've got the unknown on both sides of the equation. You have it all by itself on the left, on one side, and then you have the algebraic expression with the unknown on the other side. And so what you do is you pick a value, any value you like, for the algebraic side. That's your input side, and then the output side is the unknown all by itself. And then you feed that back in to the algebraic side, and you loop that. You keep iterating that over and over again, let's say 100 times. And as you do so, if it converges, what happens is your output keeps changing. First it's too high, and then it's too low, and then it's too high, but the high is lower than it was the last high, and then it's too low, and the low is not as low as the last one. So it keeps moving in to midline, and you can do it infinitely long. It depends how many place values to the right of the decimal point you want accuracy, and that's convergence. But divergence, the highs become higher and the lows become lower, and the thing just wants to go to infinite gain, which is very interesting because that's what these circuits are trying to do anyway. See? So this is the problem of simulators. It doesn't mean it's wrong. It just means it can't figure out what's going on. I'm assuming when it can't figure it out, the circuit is too stressed to actually maintain itself in the real world and probably will suffer problems. It might want to explode not because of infinite gain, but because of stress alone. And that's, I think, my physics definition of electrical reactance is stress, which is backwards, because the nature of the universe is electrical reactance. The nature of the universe is not electricity, in which the current and the voltage are always in phase. In fact, the nature of the universe is that they are so much out of phase that they're not even associated with each other. It's only our circuits that put them together, just like Eric Dollard says. I use him as my standard because he really knows his stuff. But when we start looking at how the simulator looks at reality, it concurs with Eric Dollard's reality. As much as he doesn't like the theoretician looking at their equations, the simulator has to be practical, it has to work, or engineers wouldn't use it. And it turns out that Eric Dollard's view of the reality, his physics version, if he was willing to call it physics, which he's not, and our conventional version of physics inside the simulator's version of physics actually concurs. They agree with each other. So the simulator's way, or the electrical engineer's way of looking at Eric Dollard's point of view, as per the simulator's point of view, is that electrical reactance is the substrate of reality. And that's probably quantum physics, what we mislabel quantum physics. Sorry for this detour, but I have to take this. It's because everything is fractionated and nothing's put together. And it's the circuit that puts it together, matter. So this implies what the Vedas say. The Vedic literature says that there was no beginning and there's no end to creation. So when we take the Creator to be eternal and immortal, his creation is also, or its creation, because the Creator is androgynous, blended male and female in total balance, be that as it may, the creation is eternal and immortal. They have to coincide. They have to coexist. There's no way you can have one without the other. And that means we, as unenlightened beings, are totally always creating. It's the field of karma. We're always creating. But our universe is imperfect, and everything we create diminishes over time. It loses potency and becomes more garbled and more chaotic. It's only when we evolve to the point that we're fully enlightened that our creations, namely our thoughts, is a galaxy, is a creation that is perfect because now our thoughts grow and evolve and become perfect beings in their own right, just as we have become. So now we can truly call ourselves Almighty Supreme Beings because our creation never diminishes. Our creations never diminish over time. They continue to grow. Well, where was I going with that? Why was I going with that? Boy, I really diverged there. Oh, so creation at its proto level of so-called quantum physics is all about electrical reactance, in which the capacitive, the reactive capacitance and the reactive inductance are diverged so completely they're not even associated with each other. We bring them together in the circuit, and the closest we can bring, or the farthest we can have them apart and still the circuit work, is negative unity power factor, in which the amperage and the voltage are 180 degrees out of phase. That's the farthest apart we can hold them together and still get the circuit to work, but the circuit is generating in that condition. And that's the ideal condition of an over-unity circuit, is to generate energy, or make it look like it's generating energy, when all technically it's doing is recycling, but per unit time. But hey, for all intents and purposes, it looks like it's generating. In fact, what we call generation is merely the transference of or the conversion of energy. Thermodynamic conversion and thermodynamic losses. So the waterfall is losing energy and it's converting into mechanical energy of the hydroelectric power plant. So all we did was convert energy. We didn't really generate energy. So we're misusing our term generation as it is. As Warren Beatty... Warren? No. What's his name? Oh, I forget his name now on Quora. I don't want to get mixed up with the actor. Actually, it might be the same name. He just spells his last name differently. I can't remember. William. I think it's William Beatty. Anyway, it is a W. That's why it's so confusing. Anyway, then as the two components of electrical reactance come closer together, let's say in a coil of wire or a capacitor, something we're accustomed to dealing with, now they're 90 degrees out of phase, the capacitive reactance and the inductive reactance. Which is the same thing as saying capacitance and inductance. They're one and the same set of terms. And then when they're zero out of phase, we call that electricity, something we can use, our appliance can use, with no losses, like a resistor or a resistive load, such as a light bulb, an incandescent light bulb. So that's where I was going with that. But I have to agree with Eric Dollard's point of view, because this is the way I look at things. And I see the simulator agrees with Eric Dollard's point of view. So people like to badmouth Eric Dollard like he doesn't know what he's talking about. He's never created an over-unity circuit. Yeah, he has. Of course he has. All the time. He's got one running under the hood of his car. For Christ's sake. I take the Lord's name in vain. Well, it's not in vain. Because God knows we could use a little help down here. Or out here, I should say. He's got a rotary electrostatic converter under the hood of his car, built by Chris Carson, or along the same lines as Chris Carson's model build. Actually, Eric built his own model and put it inside his car. And it recharges his car battery as he sits there in the middle of the desert without running his engine. So he knows how to synthesize electricity. Previously, he didn't want to admit to it, but I think because I kept pushing my simulations, he finally admitted to it. Because it's a painful period in his past. And he was burned because he made a wrong choice. It was his own fault he got burned. He burned himself because he passed up an opportunity to promote over-unity in the mainstream with the utility company furnishing electricity for Richmond, California. And he got burned at other times, too, just doing his other experiments, which subsequently after that. So it became a legacy of getting burned from that point forward. all because he didn't have the courage to go with what the manager of the Richmond utility company was showing a lot of interest in him, and offered to take him under his wing and hire him. It would have been a nice part of his career, but anyway, be that as it may. Maybe he took this. Maybe the mistake he made was the mistake he was supposed to make. Maybe he became a spiritual person at that point, and rather than a materialistic person. I don't know. It could be. I could guess that was the pivotal moment in his lifespan. Be that as it may, let's see. So these are very interesting results. So let's move on. I kind of lost track of where I got off on this tangent, but I think it was the time frame did it. Yeah. So, oh yes, matrix algebra. So when the values get too high, it becomes harder and harder to maintain the simulator in an active modality and not have it crap out on me and give me matrix is singular error messages, which is telling me it can't approximate the answer anymore, because now instead of the answer converging, it diverges. And yet the very nature of this overunity phenomenon is divergence. And so it's not a fault of the simulator that it can't handle it. So that doesn't mean matrix is singular is a fatal error in the real world. Yet, that's where I diverged. Yet, it does mean the circuit is probably so stressed that it may not be able to hold itself together and come up with consistent results. If the simulator can't come up with consistent results, why should the circuit? So if the circuit is erratic every time you run it at that point, giving you different results, probably the simulator would be giving you matrix's singular results, because I think they are equivalent realities between the simulator's reality and the real world reality. So that's why I try to avoid all errors, because they're there for a reason. This used to be a $5,000 simulator when the Spectrum software was still in business selling it, and now they just give it away for free. So to electrical engineers or anybody else who wants to make use of it. So I held out, and now it paid off. Now I get to use it for free. Before I could only use the trial version and keep my circuits very limited in scope. So that's my divergence into the realm of matrix is singular, is that you want to stay away from stressing the circuit so badly that it can't converge on a result and give you specific answers. If it can't give you answers, then the circuit probably can't, because it's so stressed, because it is so over unity. So stress actually means over unity. And again, we go back to Eric Dollig. When he took a turn for the worst and failed to go with the manager of the Richmond utility company, he was probably under so much stress he couldn't make the right decision. So that shows that his nervous system was putting out even more consciousness than it was before. You see, there's an analogy between the human specter and our machines. They are equivalent. This overunity phenomenon has everything to do with consciousness. The power of increasing our consciousness, our vibratory rate. Because isn't electrical reactance partly due to frequency? Now, they say of one of Christ's disciples, Simon Peter, as if he had a dual name like that, Simon or Peter, well, no. See, we call him Saint Peter, but in reality he was no saint. He was merely a human. Let's say that currently he's a saint, but it wasn't because of that. It wasn't at that lifespan. It was much later on in the career of his soul. Anyway, be that as it may, once a person becomes a saint, a holy man, they are more reactive than they were before and more sensitive because their frequency is higher. Now, in the case of Simon Peter, if he had become enlightened in that body, he would have had so much power because he was born strong. Remember, when he was crucified, and I think Andrew, they lasted on the cross a whole lot longer than normal. Of course, in Peter's case, he was upside down, but Andrew actually, so let's just stay with Andrew. The way I read it in the Urantia book, Andrew's physiology was so powerful that it took longer for him to die. And that means that if he had been enlightened, he would have had he would have been a very powerful saint, because he would have had a nervous system to be able to embody a greater degree of power. In other words, more capacitance, more inductance, not just more frequency. See, us lame guys like me, if I were to become enlightened, I'd be even more weak than I am now, and already I was born weak and sickly in this lifetime, so, at birth, congenitally speaking. So I couldn't help anyone. I wouldn't even be able to help myself. I'd be a dodo bird. I'd be so dumb and out of it that I would just go, and I just wouldn't be able to do anything. It's probably the reason why I keep saying, no, hell no, I don't want to become enlightened. Because I think I sense what's going to happen will happen. Because when you don't have a strong enough nervous system capable of having been engineered with lots of capacity and lots of inductance, then when you raise your frequency, your consciousness, your nervous system breaks down, and you stay locked in that breakdown condition. Even though you're enlightened, you don't have to reincarnate anymore, you're useless from that point forward until you die. So electrical reactance has a lot to say about yoga and what the Vedas say about this. So I was quoting the Vedas. What was it? Oh, shoot. Yeah, that was another divergence. What was that? Darn, I forget. Well, it's somewhere back. I think I mentioned it, but I mentioned it in passing, and I didn't linger on it very long. So I'd have to go back on the video to rewatch it to see what I had said. But anyway, so I can't elaborate. Sorry, I can't remember what I said. Some Vedic quote from the literature. Yeah, I can't remember what it is. Anyway, so there's a lot of parallelisms, and that's, I guess, why one of the reasons why I take to studying electrical phenomena now so readily than when I tried to pursue it it was 30 years ago. I tried to take it in college. I didn't handle it very well. I didn't like the preponderance of math. Now I like it that we have simulators to do all the math for us, but now I can also see, after 30 more years of meditating, I can see how to conceptualize electrical reactance in terms that are familiar to any yogi, any meditator. It's very much description of yoga, except it's happening in our circuits, if we want, over unity. So I had to take this little divergence because this is why I'm so fixated on this topic, and I probably will never become enlightened because I'm so obsessive about it, because I just love the topic. It's so entertaining as well as so educationally enriching, because it's so familiar with what I already know as a almost lifelong meditator since the age of 16. Here I am 63, so I've had plenty of time to familiarize myself with the process of yoga, and I see as it applies to electrical reactance and over unity, it's unbelievably parallelingly similar. Okay, moving right along. Here's the schematic for, what is it? Oh, now I've increased my inductive load to... No, I didn't. Whoopsie, I'm going backwards. All right. Now, here's the node voltages. I've increased... Let's see, where is it? So I've increased the resistance now to 1 mega ohm of resistance. It previously was 1 kilo ohm. That was the standard I had chosen. And here now I'm getting gigavolts on my nodes all over the place. So the node voltages have gone up. And as you'll see, oh yeah, here's tera. Where are you? Teravolts. So because the resistor is encapsulating the outward flow of current, so the voltage builds up to a greater degree. That's right. You know, that's normal behavior of a resistor or an inductor, which also exhibits resistance. Sorry for the shakes. That's what should happen when you don't have a tripod. Okay, now which way am I supposed to go? Is that the right way? Yeah. So there's the schematic. Now here's the 1 mega ohm resistive load. It's actually gone up. See? So now we have, oh, I didn't say the amount, the spikes. What is that spike? It's over a mega amp. The spike is now peaking over a mega amp in both directions. Oh, now it's in both directions. Whoops, so much for unidirectional. Uh-oh. Oh well, that's not entirely always true. Oops, wrong direction. Yeah, this is unidirectional, and the spike goes up just underneath 225 kiloamps. But this one goes in both directions and is just underneath 2 mega amps. So we continue onward, and the next one is when we increase the inductive load to 1,000 henries, and now it goes back to being unidirectional again. Even though we maintain the resistance at the previous value of 1 mega ohm instead of the prior value to that one of 1 kilo ohm. So now we've reduced the outcome, though, because it's soaking it up. The inductive load and the resistive load is dissipating all that extra energy. So now the resistive load has dropped back down to just under 300 amps of that it is embodying. And so now let's see. Oh no, this is the the node voltages. The node voltages are still pretty high, gigavolts. No tera. The tera has disappeared. And here's the schematic. Now, when I raise the capacitive load to 31 farads from 10 farads, the amperage on the resistor drops even further. Now it's under 12 amps. And they're unidirectional spikes. So apparently if you go too high, it goes back to being bidirectional spikes. But if they stay within a certain limit, they become like a diode, unidirectional, for the most part. So that concludes, yeah, that's it. So I have nothing more to cover. Pretty interesting. I'm going to put all these files into this simple analog computer zip file at is.gd/simple analog.